Thank you. Thank you so much. So, with the motivation to struggle mocks on groups, and more specifically on hyperbolic groups. So these are joint groups. And plane 2. It's two different results which are related actually. So we begin with the motivation, my motivation, one of the motivation. So I will begin with classical probability theory and just interrupt me. So I will go back to probability theory and the concentration phenomenon, the bounded difference inequality. Also called Magdianite inequality. I think I'm not so specific about each one because it's a folklore. So it's a property of the product measure. If you have spaces y1 endowed with probability measures mu1, and I do the product for necessarily the same. I take xi, iid, independent random variables, respectively on yi with respect to ui. And the goal is to study how much a function on the space, a function of n coordinates concentrates around the expectation. So how much f of x1, xn, so these are, let's say, endpoints distributed with respect to mu1, mun, how does it concentrate on a function of my n tuple? And so this will depend on my function, but the concentration phenomenon is to try to do it for a large class of functions. So the probability of this bigger than t is smaller than 2 times 2 because there is the absolute value, right, left, 2 minus t squared times a constant that depends on f. So what are the class of functions f which are allowed? And for this inequality, Lipschitz with respect to each value. So f.
F cannot be one function, it's Fn, because f cannot be one function.
Yeah.
So what does it mean, Cf?
Yes, thank you. It's a Cn, yeah, it's a Cn, yeah.
Okay.
Yeah. Okay. And it's true for any n, for any t. So, and later we will play. Okay. What is f? This is a Cn of f.
But I'm saying it's Fn because how can you have one function of n variables? So it's kind of Fn. I don't know what means f. One function that you can apply to as many variables as you want.
Okay.
What does it mean?
I'm fixing n.
Okay.
I'm fixing n. Okay. But it's true that later I can take n big enough and add different bigger, and my function can vary. Yes.
Okay. Thank you.
But typically, yeah, in the head it's an Fn. But n is fixed. It's a high dimension, let's say, phenomenon. So n is fixed. Thank you. And f of x1 I. So with respect to if I vary just one coordinate, I should be able to control it by a constant Ci. And this should be for any point, for any. And in that case, the constant is L2 norm, the L2 norm.
You mean Ci times xi minus x prime I? You said Lipschitz.
Okay, sorry. So I'm not putting a metric. So Lipschitz in the head that it's an abuse of notation. I'm not putting. I could have put, but
Okay.
I'm just putting the discrete metric. But I'm not putting a metric. And it's true for any n, for any f. So the typical application is for the sum.
Xi are living in R, a real number.
For
Xi are, where would they live? Xi are a random variable from random functions. They are real random variables.
the function is real, but the variable can be. It's like
it goes from where to where? From
the xi. These are probability spaces, abstract probability.
Ui are probability measure on yi.
On yi. And
xi is a function from yi to the real number.
yes.
Okay.
Yes.
So f is a function on r cos r cos r.
F is a function from ym.
What? Okay, I go on, but I don't understand.
Okay. Okay. This is a prob. This is not necessarily real number. Okay. It's a product of. It's a property of the product measured on this space. Dictated by the properties of a real valued function on it. It's like assisted dynamic, let's say.
Go and I think I understand it.
And this is my random variable. This is my random variable. It's mu2, mu1 tensor mu_n. And the set of stem in the abstract space such that f is minus its. This is the right hand side. This is the left hand side. Typical example, if say R in this case, I see it as a property of a measure.
This I understand.
No, but
Okay, go ahead.
Okay.
I understand that.
Now I take this sum. And what does it mean to be Lipschitz in this set? In this sense, it means that. So I restrict that each coordinate. Yes, exactly. So we obtain that if xi are between ai and bi bounded random variables, almost should then probability sum minus n times application. Now I will change this. Is true for any t for any n. I will put nt here. So instead of t, I put nt. And the Lipschitz, the CI is BI minus AI. Okay, so this is how a classical random walk with increments which are bounded concentrate around its expected value.
This is the classical Azuma.
Yes, Yes. And the message I wanted to say is that if I have a function of independent random variable other than sum, also I can think of applying this with a suitable function, but maybe the constant as reported out can explode, I mean, in some sense. Now, what's good about these inequalities that these are finite time estimated. It means that it's true for any n, it's true for any t. If we want to go to asymptotic, so I fix t and I let n goes to infinity, the series converge by Bora and I can recover, I mean, with this assumption, which is not the optimal, I can recover the strong load of large number. So it's a almost sure convergence. Now, if it was not exponential but summable, I would recover the weak low of large numbers. So this is one aspect of asymptotic. Another aspect I want to point out is the t-square. So t-square, when this probability is really...
But what is good is the law of large number where you don't assume identically distributed. You do not assume that better.
Oh yeah, yes. So if I want, when this is really strictly less than 1, what is the range of t? It's when it's of the order 1 over root n. Where I can see, let's say, a probability which is less than 1. So, which means that the typical speed of concentration is 1 over root n. So it goes in the direction of the central limit theorem. And the constant implies in the big O depends on these. So that's why it's not a so good inequality. It should because it should imply the variance. So maybe that's not the best inequality, and that's why there are other inequalities like Bennett-Bernstein inequality that I will not mention. That gives you a better estimate here. So this is just the preliminary of the probabilistic setting about concentration inequalities. In statistics, definitely it's used to have confidence to estimate this usually unknown, and this also will play a role in what I will say. So the second is the framework. So how it began. So the title of my talk is about random walks on hyperbolic spaces, but I will focus on matrices and let the hyperbolic setting come naturally. Great. So I will run for now in any dimension. I will by G the general linear group D by D invertible matrices. I will have a probability measure on G, but typically in my head it will be a finitely supported measure. So the support of mu, which will be denoted by S, will be finite, and my finitely generated group will be denoted by gamma. Typical example, S. Two matrices that generate Sn2Z as a group. And I will do a random walk with in S. So for instance, mu, you can have half or 1/3 and random walk. I will take them IID. I will take them IID with row mu, and so I'm just multiplying. So it's a way, non-commutative random walk. That definitely I can do the other way around, and we do not expect for them to have the same behavior. And what will replace the sum of the xi, which is, it will be the, so I will denote by kappa n, the log norm. I fix a norm. And this quantity, which will be the quantity I wanted to concentrate. And what is the law of large numbers? It's just here. There is a normal Schur conversion. So the norm behaves exponent. This is the exponential growth of the norm. So the linear growth of the log norm. This is the top Yapon of exponent. And as you see that really does not follow from the classical law of large numbers, because this is not additive, this is sub-additive. So this follows historically, this is a theorem of Furstenberg and Sexton in the 60s. And now this sub-additivity, we see it as a result, as a consequence of a general ergodic theorem, Kingman sub-additive ergodic theorem. It's a consequence. So function, I take the infinite tuples. So I have a dynamical system, g to the power n. I have the shift on it, and the log norm has this sub-additivity. And by Kingman sub-additive ergodic theorem, it implies that there is a limit. But Fn of omega is this. Fn of omega over n converges. And the same that is this Yapon of exponent is a bit mysterious. We do not have a closed formula for it. And my goal is to have concentration estimates of this around the Yapon of exponent. This is one way of understanding the exponent itself, because I do not have a closed formula for the Yapon of exponent. So the goal is to have a concentration inequalities for kappa and n of exponent, finite time estimates for the moment. Historically, Lepage give exponential large deviation estimates under some conditions. So under algebraic conditions on the group generated, which are strongly irreducible and proximal, since I will not use them a lot, I will not say them, I will not explain them, but they are satisfied in the example of motivation. The page proves the following. Was it T? Yes, it was a T. So here there is quantificators. All T, for all N large enough, and for all T there exists a constant. And with respect, the support needs not to be finite. The support needs not to be finite. So the positivity of this constant already imply, it's a strengthening of the strong law of large number because it's exponential, but it's not a finite time estimate. Which means that I cannot use it to understand my Lyapunov exponent in terms of this. So these are exponential large deviations estimates. So I should wait a lot in order to have.
It's some kind of epsilon. You think of T as being epsilon.
Yeah, but I wanted to see, did I use epsilon or T? Yeah,
You use T, but
yeah.
T being small.
Yeah. Yes. Yeah, I'm thinking of it of being small, yes, but also in concentration, we can be interested in T big also in terms of scale of. Okay. And one question is to have a quantitative version of this, understanding C of T, is it of the 40 square, etc. What are the constants implied there? And till now, we couldn't manage to have it in this generality.
Yes, but for this inequality, when you know it for T, and more and more difficult when T is smaller and smaller of this inequality. It depends if you want to have a specific formula for C.
Exactly. So if I have it for small enough, I have it for big enough, but
if you want to have a better C, then you have to find.
But already for small enough, and for small enough, yeah, using the ingredients, the techniques of Lepage, which are analytic perturbation, I can have the T-square. Okay. I can have the spectral methods. I can have the T-square. Yes. Okay. But the constants are not here.
Okay.
So
C times T square for some. For some constant depending on the C.
On the measure.
The measure.
And these are specifically what we want to study. And the time N. And the time N. So the first result I want to talk about, we said, is finite time estimates in the case of SL2R, in the case of fiction groups. So it is in this order that we managed to obtain explicit results. So I have gamma. So discrete, non-elementary. So discrete, non-elementary, it has two elements, two hyperbolic elements, which are in general position, or it's Zariski dance, or also it does not preserve any line or any finite union of them. Finitely generated. It's finite. And these are, and mu a probability on S, who support S. Then minus more space. So, like in the usual Aoun 15, I should have some. Oh, it's erased. I should have. So it's an exponential decay. I should have something related to the. It was bi minus ai, the size of the support. I will call it kappa of. Call it as. Log. There is a logarithmic term, and I will denote by as.
Like as what? What do you want?
Logarithm. There is a small logarithmic term.
Okay.
And as is the max s. So the maximum time. This
Kappa s is log of the norm. Kappa s is log of the norm.
Yes, kappa s is log. So there is a square like in the usual, but there is another term depending on the measure, and I want to understand it. This also depends on the measure. And I will call it mu with some constant which is universal.
It's times or it's plus? Times.
With mu just the minimum. So, I mean, if it's the uniform measure, it's just 1 over the cardinality. So it's really an explicit formula. And it's not a surprise that the fact that it acts by isometry on the upper half plane would play a role. But not also this. I mean, it's a combination. The fact that we have it explicit, it's a combination that of the linear structure plus the fact that it's as a group of isometries of a hyperbolic space. And as a consequence, so we know that by this alternative, that such group contains free groups of non-abelian free group over on two generators. That corollary, same assumption. If I take 2 random more, which are independent, so Ln and which are independent, the increments are independent, the probability that the subgroup is free goes to 1 exponentially fast, but with constants that we can compute. So let's say it's T of mu, which is very explicit. And the consequence is that I have an information. Okay, T of mu does not depend on S. So as we see here, I mean, the dependence on S is only over mu of S. It does not depend on gamma. So let's say it's fix the number of generators, just alpha. So it gives me that there exists I'm quantifying. Okay, let me put it like that. It's related, and an ingredient of the proof is the strong Tix alternative of Rayard. So I'm putting history before commenting on this. Which tells you that not only with this assumption, in any dimension, no assumption on the action, in any dimension, if gamma is non-amenable, linear group. Actually generated linear group. But I fix the dimension. I'm in GLD. There exists an alpha that depends only on D, such that this s to the power n0, s to the power n0 contains contains a free group on two generators. So it's a strong text alternative because the N0 does not depend neither on the generating set nor on the subgroup generated. And this result is a tool and the proof of it, but it's also, this gives the other way a strengthening of it in the sense that I can know the proportion. I can say that the proportion of couples in S to the power this N0 that generate a free group is exponentially big with an exponential rate that does not depend on anything. Because I'd say the proportion of
the proportion of the home pair are exponentially small.
Yes. Okay. And the exponentially small is so in my thesis, I have proved the similar result, but without explicit constant in any dimension. And the goal was to have explicit constants. And I mean, that's one of the motivation.
Uh, 10 minutes.
Okay. So the result is a particular case actually of a more general result in the following sense. More general. And it will be clear how these constants appear. More general. If I have M, a proper metric space, and G, its isometry group, which is now locally compacted as its third measure. Gamma is a group of isometry of M. I will assume, so it should be here, I will assume M to be Gromov hyperbolic. In the sense, it's a geodesic, I will take a geodesic. It's a sense that triangles are delta thin. The union of delta neighborhoods of any two geodesics, in a triangle will cover the third one. And what's the relation with that is with what I said before, M is the upper half plane. G is into R. As a group of it. And I will take it non-elementary. And we can ask the same question. I do a random walk. Which is distance of my random walk, base point, fixed base point. And I can ask the same questions. And so is the framework okay? So I have a finitely generated subgroup of isometries of a hyperbolic space, and which is non-elementary. And the case, the example of matrices as L2Z, for instance, fits in this picture. And also you can have a random, you can have hyperbolic loop and have a random loop on its scaling graph.
There is no discreteness.
Hmm?
There is no discreteness.
Okay, so yeah, so what do I assume exactly? The more I assume, the more I will have quantitative things. So I started the one with SFR first because I like matrices, but also this is the framework what I will have basically a lot of quantitative things.
Do you have something for SFDR?
No,
No.
no. And actually, just for the history is that I have this. I mean, this problem was here in my head sometime, and it's when I read.
Your thesis is for SLDR.
Yes.
Yeah, but for this explicit constant, you just know SL2R. Right?
Yes, and the thing is that when we encountered your paper with Benoit's central limit theorem on hyperbolic space, the last section, when you prove regularity of the measure with another method, I mean, which is independent, that I mean, all the things came. So this is a framework, it's transversal, so it does not cover, since I'm assuming hyperbolic, it does not cover any dimension, but definitely it covers a wide range of geometric spaces and randomness. And the same is, I will assume, so this is really inspired by the paper of Benoit and Aoun, supplementary probability. To be big, to be acting co-compactly. Was the case. Now, if I do not assume discrete, I have a constant without discreteness. The right-hand side of the function, okay, what I'm interested in concentrating kappa. So the size of the support is still here. Now, what is the constant here, which was the mu, is the gap, the gap of amenability. So it's 1 over the norm of mu in the regular representation of the big G. So I will explain. Because M was proper, G was locally compact. I talk about its R measure, and I act mu operator acting on two functions. Like it's mu of S, G times F. And this is a contracting operator, and we know that, but it's on the core of G, we know that so this is a generalization of Keston's result. So it's Keston and Christensen. Non-amenable as, so P mu is strictly less than 1, if and only if it's the group generated by V and its inverse is non-amenable as a locally compact group. And the discreteness assumption is to go back to the intrinsic regular representation on the group itself, on the countable group itself. So this quantity, we do not control it a lot. I mean, mu, you can have, it can be supported on a free group, but the free group can be very close to identity. So this will explode. So in order to have something more quantitative, if we assume discreteness, I can go from G to them. Once I go, so this is discrete, how discreteness is used, but without discreteness, there is this. This is the gap of, the more it's, the result is, say, the more I'm non-amenable, the better the concentration is. Second thing, for hyperbolic groups, by results, okay, no, before saying that, so discreteness, let me pass from lambda g to lambda gamma L2, or lambda mu, and L2g to L2 gamma. And then by the same, basically, proof of, so in each talk, we wanted to find some particular nice abelian group in his case. In my case, I want to find some nice free group inside some big power. By doing the same trick, I can bound. So I will. So now, if I assume, so now here I'm explaining how do I go from this result to the result of SL2R. So if we are discrete, how do I control this? But I go to some power of n, I find every group there. This will be 1 minus the minimum of the support in Eve was just all the probe, this alpha, mu of the spectral radius of a free group, which by Peston we know it's a universal constant. So should I stop? Yes. Yes. Okay. And that's it. I wanted to say more, but definitely I didn't have the time. Just to say that the idea of now this is a geometric setting, but how do we obtain this? How do we obtain this? Is going back, is solving a cohomological equation. Basically, idea, just 1 minute that I will stop. Idea, this behaves like a martingale. So the sum of ideal random variable is a martingale. But so this is a more generation plus a big O of 1. A big O of 1, it's a random constant that's really independent, bounded, uniformly bounded. And all, now I should use Azuma Hafting here. There is an Azuma Hafting for martingales. Now, how I prove this? Look, this by solving a cohomological equation. Lepage and Benoit. But all of this works in n dimension. The thing is how the constant will be the bounds here. This constant that is the bounds here. And we used the form of the solution of the cohomological equation given by Benoit related to a regularity of a stationary measure on the boundary. And here, so the big O of 1 is basically the integral of the Gromov product. And to control, there is the harmonic measure on the boundary, and to control its regularity. Basically, the geometry helps us here in controlling the. It's non-atomic. It's non-atomic. This goes to infinity if x and y belongs to the same infinite geodesy, but it's not atomic. But how much it gives mass to balls? So it's related to this by this is related to the spectral gap by geometry. Delta thing. So I didn't have the time to talk about another word, but thank you.
Questions?
This is for any Gromov hyperbolic metric space. Your US.
The group needs not to be Gromov hyperbolic.
But yeah, okay. But group of isometry on any
Yes.
Gromov hyperbolic space.
Proper.
Proper.
If it's not proper,
Okay.
we can still solve the combinatorial equation. I mean, in your paper, you did it for proper, but
Yes.
Orbas verified. So, but it gives the t-square, but I cannot relate it to, because G is no more locally compact. And it just gives an ugly constant, but it gives the local t-square behavior, which means in the rate function it's quadratic. That's what I wanted to.
Okay.
Other comments or questions? Maybe something comes through.
Any questions from those on Zoom?
I don't know if George is in
All right, it looks like no questions from Zoom.
There's an equation. So, and what if you want to weaken the heterogeneity assumption? In what context, general context, one can expect something like this?
Okay, if I want to say matrices, really, I have no idea because the geometry of the symmetric spaces, I mean, I do not understand it. But I think from a combinatorial group theoretic point of view, we can maybe, I don't know, free products of, yeah, I do not have a clear, but I mean, I think I take weakening, let's say, this works for a Gromov hyperbolic group, for instance. So I'm pretty sure that maybe extension of hyperbolic spaces in some sense. I do not have a clear. I mean, the method is not new. It's solving a homological equation. The method is here. Solving. I mean, this method, and I'm not saying that this is the optimal method. Just that the homologic equation was mostly used to prove central limit theorem. We used it here for concentrations, but it's about controlling this.
Or maybe on the contrary, if your group is not a low hyperbolic, can you comment? Can we have something really very different for your question? Like a group that which is not hyperbolic.
I mean, on the quantitative side, I don't know. On the qualitative side, yes, because even in any dimension, this works. It's just that this constant, even if it's not hyperbolic, even this constant is just a constant on me, and that's it. So, for instance, random walks on mapping class group that was done by Corbett, I think that I'm pretty sure that we can extend what was done for the random walks on the mapping class group. But also the question is how to quantify. It depends what do we want. If you want asymptotic results, then this is fine.
If there are no questions, let's thank the speaker and all the three speakers of this afternoon for interesting talks.